Hello everyone, my name is Felienne. I'm assistant professor at Delft University of Technology, that's in the Netherlands. I'm on Twitter as well, this is my Twitter handle, and if you rather read the slides than listen to me talk about them, they're already on my website, so you can go there to check them out or share them with your friends. So this is, oops, I forgot to enable my clicker. So this is what normal programming looks like. You start with a problem, and then you think very hard, and smoke comes out of your head. That's me thinking about a program. And then at one point, you have the solution, and then you write your program. Which is nice when you're at the light bulb stage, but that stage is sort of not so very fun. So let me tell you about program derivation, because how program derivation goes is like this. You have a problem. That's not a problem yet, and then you just write a specification, and look how you're still happy because writing a specification isn't so bad. And then you take your specification and you derive a program from it, which is a fun exercise where you use your math skills and you're still happy. And then from the derivation, you just for free get a program. And then you're happy as well. No frustration, happiness everywhere. And the nice thing is also that because you have derived your program, it's by definition correct. So you don't need verification, you don't need model checking, you don't need testing, because you know the program is correct because it came directly from the specification. So that's kind of abstract. Let's look at a simple example. Suppose we want to calculate this secret super value by summing all the numbers from 0 to n minus 1. So remember the steps I talked about a little while ago. The first thing we need after we have a problem is we need to write a specification. So if we want to sum all the values from 0 to n minus 1, then we can write that in sort of mathematical language like this. We have the sum of I from 0 to, this should actually be a smaller than, it will be fixed in subsequent slides, smaller than n. And what we're summing is the value I. So we just take all the numbers from 0 to n minus 1, and what we're summing is the I in the middle. So I have a super special thing that no one else has in the world. I have a version of ReSharper that works on my handwriting. So what we can do is we can refactor this specification a little bit according to features that you probably already know if you use ReSharper. If I right-click that n right there, this comes out. So what I can do is I can refactor and I can introduce a parameter. This is not something new if you've used refactoring tools before. And my version of ReSharper is like, okay, you want to refactor that n, that's fine. We can make it a parameter, so that's small n right there. And then you click next, and then this is what you get. So this is actually a program derivation technique called generalization, but you already know this because this is just the introduced parameter. So nothing strange has happened here. I'm just saying that instead of summing for this exact value, big N, I want to have a more general function that sums for small n. And of course, if I want the concrete value, big N, I just put the big N in. So one thing is, I have handwritten all of these slides, and I'm really very bad at drawing brackets. I never get them right. They're not symmetrical, and then I erase them and I make them anew. So just to save me from some frustration, instead of using this for function application, I just use a dot because it's easier to write. And it's also common in some programming languages, so I hope it doesn't confuse anyone. So we have a specification now. The specification is nice and general. So let's just do some calculation. Let's just torture this specification long enough until a program comes out. So this flag is something like a scope. So I'm defining n is now 0, and within that flag, everything that goes here, there I assume that n is 0. So if n is 0 and I want to calculate my secret super value of 0, what I can just do is take the definition that you have all the way up there and substitute it. So this is just the definition repeated, but instead of the n, I now put in the 0. That's still quite simple. And now you can see that if I would have to point at such an I between 0 smaller or equal to I smaller than 0, there is no such I. I cannot find an I that's both bigger than 0 and smaller than 0. So that is the empty domain. And of course, if I sum the empty domain, if I take the sum of all these 0 numbers I have, that is 0. So the case for n is 0 is pretty easy. Let's continue. What comes after 0? Well, let's do the case for n is 1. This is the secret super value of 1. I could do a similar calculation, but here's my efficiency turtle, and he says, is it really a good idea to do this for all natural numbers because we don't know how big our small n is? It could be really big. And if a turtle tells you you're not being very efficient, then probably you should listen. And my turtle has some interesting insights as well. My turtle says, well, if I can reach 0, and if I can make a step of 1, I can reach all the natural numbers. So if I'm at 0, and I already showed you that 0 was covered because the sum of 0 is 0, and I can also do a hop of 1, that means I can reach any number that I want. So I just have to prove it for 0 and the +1 case, and then I've got all the natural numbers covered. My turtle can reach all of the numbers. Look, there he goes. Vroom. Super quick. So one more thing that's really important to understand about this is that because the only operation I have is the +1 hop, if I'm at, let's say, 5, I may assume that I once was at 4. Because the only operation I have is the hop operation. It wasn't like a spaceship dropped me at 5. And this is called the induction hypothesis. And this is something that we will use in all of the proofs, that if we have a problem that's smaller, we may assume that we already have solved that. So let's use some induction. We're now going to look not at n is 1, but at n is n+1. Again, we have the secret super value, and this is our induction hypothesis. So what we can do is we substitute again this definition, an n with an n+1, and then we get this. So now observe that if I is smaller than n+1, that means either I is smaller than 1, or I is n. So it cannot be the case that n is something else. Either the highest it can be is n. So either I is n, or I is smaller than n. And this is called a range split. So we can split the range. We're summing all these numbers and we're chopping it up. So either we have the situation where I is smaller than n, or I is exactly n. So here, this is a singleton domain that looks very much like the empty domain. So we're not summing 0 numbers, which is 0. We're summing exactly 1 number, which is very easy. Then you just get that 1 number. So that replacement is doable. And then what do we see there on the left-hand side? What is that? Look at that. That is the induction hypothesis. And n is smaller than n+1. So we're in the case n+1. And we now have derived something for n, and which is smaller. So we may just replace that with a call to the secret super value of n. So now we have a definition for the case n+1. And then together we have 0 and n+1. That gives us a solution for all the natural numbers. So Houston, we have a program. Isn't that nice? So this is our program. We have, if n is 0, it's 0, and otherwise we do a recursive call to one value lower, and we add this value -1. So that came out without any thinking. Observe how there was no smoke coming from my ears thinking about this. I just derived the program and it came out. But yeah, of course, some of you might have been thinking, yes, but I can come up with such a small program. If I just need to sum a few numbers, then that's easy. You don't really need the power of program derivation. Yeah, okay, that's true. So let me show you something more cool that, well, algorithms you know, but you don't know the derivation for. So I'm going to show you 2 sorting algorithms for the price of 1. First, what is sorting? So I'm defining here a function called allElements. Don't think about it too much. The allElements function just goes from a list to a bag, which is like a list but doesn't assume anything about ordering. And if I take an empty list, I get the empty bag. If I take a list of length 1, I get exact that element. And if I have a list that consists of 2 sublists, I'm just going to do, this is a union of bags, take all the elements of the one and all the elements of the other. So don't overthink it. This just says all the elements in the list in no particular order. I also have a function, isAscending, also similar, you understand what it means. A list is ascending if I take 2 items out of the list, and if this one comes before the other one, and this one is always at most that value. So it's just in ascending orders. With those 2 definitions, I can specify exactly what it is to sort a list. The sorting algorithm goes from a bag to a list, and all of the elements, for any bag I take, all the elements of the sorted list are equal to that list, and the sorted list is ascending. And this basically means no one is stealing anything, and at the end everything is in ascending order. That's what the definition means. So, again, we have a specification. What are we going to do? Not thinking. Thinking is forbidden. We're just going to use mathematical rules to derive a program. And really, I encourage you to try this for yourself. It's very, very hard not to think. It's surprisingly hard to mechanically derive a program and not think, oh, I know where this is going. So for this talk, because they only gave me 30 minutes, I'm just going to focus on the first half of the specification. So forget about the second half for a while. I'm only looking at the first half, the no one is stealing elements half. So what I'm going to do here is I will do induction on the bag. And initially we did induction on the natural numbers, where I said you start with 0 and you have a +1 to reach bigger natural numbers. So for bags, the situation is we start with the empty bag, and the making the situation bigger scenario is where you have two bags together, the plus. So we look at the empty bag. What do we have? All elements of a sorted empty bag should be equal to the empty bag. So let's go back. Oh yeah, if we're here, there's nothing really that we can do. So I'm looking at this, I don't know what to do. But if I go back to the specification of all elements, I observe that there is an empty bag. So probably I can use that. I don't know where I'm going yet, but this is an equality I have. There's an empty bag here, and I know that an empty bag is equal to the all elements of the empty list. So let's just substitute that and see where it goes. Now, at least on both sides, we have all elements. So what we need to do now, suppose we need to make this true. We need to make the sort of the empty bag, the all elements of that, equal to the all elements of the empty list. Well, we could make that true by putting the exact same thing in. So it's maybe slightly confusing, but mathematical functions, pure functions, if you put the same thing in, the same thing will come out. So if these two need to be equal, if I just say, well, if only those two were equal to each other, and then I apply a function, then the result also must be equal. So I can make this true by just defining the sorted empty bag is the empty list. This is a choice. I could do other things, but of course in this talk I'm only doing the happy path that immediately leads to something. So this was the base case, and now we're looking at the situation where we want to make our bag bigger. So we have a bag that is S plus T divided in some way. So this is what we need to make true. All elements of the sorted S plus T should be equal to S plus T. Remember again, this is our induction hypothesis, and we could use that because for all bags, we know this already holds. If it would only be the case that B would be strictly smaller than S plus T. So this is the situation where we're at 5, and we're looking what is smaller than 5. So S plus T is our 5, and what is smaller that we already know that it holds for, that is S or T. Both of them are smaller, if only they wouldn't be empty. So we're looking at the situation back. So I may substitute S by all elements of S only if T is not empty, because if T would be empty, then S would be the whole list. So assuming that I split it up nicely in the middle and not one of the halves is empty, I can use the induction hypothesis, and I could use the same at the other side. What comes now is maybe the most confusing part of the talk. You entered at right the exact perfect time. So this is maybe the most confusing. So don't be disappointed if you don't immediately understand it. What I'm going to do now is I'm stuck. I don't have any rules anymore that I can mathematically apply. So I'm just going to invent a solution. I'm saying, well, if there would be a function called plusl that would specify this. So for the plusl, it would be true that all elements of sort S plus all elements of sort T would be equal to S plus T. I'm just inventing that plusl. Well, then my problem is solved. So I'm just introducing a function, and I say, this is mathematics. You can just invent stuff, and it works. So I have a sorting algorithm. We are done. If X is the empty bag, we have the empty list. If X is the singleton bag, we get the singleton list. And if X is two sub-bags, I'm just going to plusl the sorted versions of them. And we're done. Yay! Any questions? Yeah, the bunny is also confused because what is the plusl? I don't know yet. So I still, if I want to have a real algorithm, you could stop here, but if I want something that I can put into a computer, then I need to find a definition for plusl as well. So what must plusl follow? We just defined it in exactly this way. So all the elements of S plusl T must be equal to all the elements of S plus all the elements of T. And remember how I told you that I'm only looking at the first part of the equation? If I'm also doing the same exercise, if you want to do it, you could try this at home. If I focus on the second half, then I get this specification for the puzzle as an extra requirement, and from now on we are going to take that into account as well. So I just trust you that you trust me that that is the actual requirement. So does anyone have any ideas for the puzzle? There might be an operator that we already know and that has occurred already maybe in this presentation that we could use as a candidate puzzle.
Merge.
Plus, concatenation, yes, absolutely. So if you look at the structure, you might think, oh, concatenation could be a good choice. And again, I'm doing, wait for it. Again, I'm doing only the happy paths in this presentation. Of course, there are lots of things you could choose, but let's see what happens if we use list concatenation. Are we then there yet? And I already have someone here that's disagreeing with me, so that is awesome. So that first part, is that first part okay?
Yes.
Yes, my spider agrees. This seems legit. I'm not proving it. As we professionals call it, this is a proof by hand waving, but you can see that this is true if you just concatenate to a list and no one is stealing anything. So I guess your beef is with this one then.
Yeah.
Yeah, it's not really true, is it? Can you give an example of an SNT for which this is untrue?
1, 4, 2, 3.
1, 4, 2, 3. Yes, that's a fine example. So the first thing is ascending, 1, 4, and 2, 3 is ascending. But if we glue them together, then the whole thing is not really ascending. You got that very well. So do you have also a solution in mind, maybe? Because I can tell you that we can add one conjunct right there where my question mark is, and then everything would be fine.
If S is inferior, if all of S is inferior to all of T.
Fantastic! So if we split up the list, if just all of the elements on the left side would be smaller or equal to all of the elements of the other half of the split, then it would be fine. And again, I assume you trust me, you can prove this, but I don't have the time for that. So if we have that, then our problem is solved. So, we have an algorithm. Again, this is as we already had it. And suppose we're in the happy case where the one list has smaller elements than the other list, then we can just puzzle them. Happy?
Yeah. Quick sort.
Yeah. Next time say spoiler alert. Because we aren't done yet. Because this is definitely not quick sort. Because what are we going to do when we get to bags of which they don't follow the specification? What do we do then?
Partition. Yeah.
Our bear isn't happy. So we don't know what to do. We don't have a solution for that. But of course, we are computer scientists, master of the universes. We can just make it so. So suppose we just have a partition function. Spoiler. If we have a partition function, we're just going to partition our list in such a way that we got the smaller items on this side and the bigger items on that side. Then we have an algorithm. And this is an algorithm that some people might know as
quicksort.
Yes, you can say it now, quicksort. So we have formally derived quicksort. But of course, as you have remembered maybe from the beginning of my talk, I promised you 2 sorting algorithms for the price of 1. So we're going back to the point in my talk where we were here. So forget about the fact that concatenation is a candidate for puzzle, and we're going to start again from this higher level specification and derive another sorting algorithm. Isn't that cool? Because my boss is Scrooge McDuck, and he only wants to pay for 1 recursive call. So he says, no, you can just do 1 recursive call, because 2 recursive calls are way too expensive. So we're slightly going to change our definition. Maybe someone was already considering that, but what actually is the type signature of the puzzle? Has someone thought about what exactly a puzzle does?
List.
Yes, my fly agrees. It's list to list. So if we're now in the situation where we cannot do a recursive call on the S anymore, then S is 1 item, because we cannot use a bigger list because we may not recurse. So we're in a situation where the length of S is exactly 1, and we have to make sort S puzzle sort T. So we can observe that if we sort a list of element 1 by the definition of sort, that is equal to that element. If you have a list of 1, it's already sorted. That is sort of simple. And now we can say the list of S consists of one element. So I can always give that element a name. So this is the exists. There must exist a B for which S is equal to the list of B. Which is, I'm just saying here, if this is a bit confusing to you, whatever is in the list of L, that element, I'm calling it B. So what we're looking at now is the list of B plus all sort of T. And we can change that by introducing a times all that takes, instead of a list, we chop off the brackets here, takes an element and a list and makes another list. And then we are taking an element and a list instead of a list, so we just have one recursive call. So we say we have the B times all the sort of T. So what is the times all? It's very much like the plus all, only a little bit different. It still must obey the same rules. Does anyone have any ideas what the times all could be if we're thinking of an element and a list? What is a famous function that takes an element and a list and creates a list? Cons, yeah. You are banned from further speaking. Cons. What about cons? Cons looks like it might be in the right direction. But first, let me bring in my simplification butterfly, because since we have a list of 1, we can make our definition slightly smaller, because all elements of one list, that is guaranteed to be that one element, and an element is always ascending. So those we can remove, and then we have a slightly simpler specification for our times all, which is like the cons. So again, this first option, I believe that. If I have all the elements of a list and I add one element, I have all the elements of that list plus that one element. This, however, who buys this? If I have a list that is ascending and I have an element, so for instance I have 2, 3, 4, and here I have 7. If I cons the 7, then it's not ascending. So we have to again make it so. We are going to make a times all that looks very much like the cons with a few slight modification in order such that this equation is exactly true. So this is a definition of is ascending, and again here we're going to use induction, and we're going to do induction on the T. So if this T is the empty list, then it's sort of easy. Suppose we have a T which is the empty list that is ascending, which it is, then we can easily make the list of B cons the empty list ascending, because that's just a one element B which is always ascending. So this case is very simple. Here we can just use the cons as our times. The spider is happy. So our induction hypothesis now is that if T is ascending, that implies that B times all T is also ascending, if it's smaller than the situation we are in. So we take a bigger situation, and in the case of cons, that is, of course, is H cons T. So there are two options now. Either our B, the one that we're trying to get into the list, is smaller or equal to the head of the list. That is the happy path, because in that case we can just cons the B in the list. And we have 3, 4, 5, and we have 1, and we glue it together. But what happens if the B is bigger than the head of the list? Any ideas?
Recurse.
Yes! Did someone say induction hypothesis? Our T here is strictly smaller than H of T. So we can do a times all on the T because it's smaller. So what we can do is we put the H and then we take the B and we times all it right in the rest of the tail. And now we have this. This is as we already had it. And our sorting algorithm is we take an element and we times all it with the sorted tail, and this is the time. So it's just an empty list is adding the B to the empty list, which is the list of B, and otherwise we're either putting this B in the beginning of the list, or if it's bigger, then we push it further on. And this is
Bubble sort.
Insertion sort. It makes me feel slightly happy that you got that wrong. This is insertion sort. So look what math has brought us. We have now learned that insertion sort is a special case of quicksort, because they both follow the same higher level specification of a sorting algorithm. And just by making changes in how you implement the rest of the proof, you get different sorting algorithms. And you can do a similar thing for merge sort that also follows the same specification if you make different changes, but that definitely didn't fit in this talk. So a few takeaways before we go. I don't know, John, is there time for Q&A? There's some time for Q&A. Awesome. So before we go to Q&A, a few takeaways that I would like you to remember. So programming is math. I know people that are programmers and they're like, yeah, but I'm bad at math, but it doesn't matter because I can program. Well, there's math and there's math. Of course, maybe you don't need calculus or differential equations for programming, but logic and set theory are really the basics underneath computer science. And of course, this is maybe a bit too strong. Let me change that into programming implies math, because of course programming is way more. It's also creativity and design. It's not equal, but at least there's a part of mathematics in programming, and we shouldn't forget about that because it can bring us great things. Calculation provides insight. So it's not necessarily, of course, the case that you should do this in your job every day and say, wait a minute, I'm going to derive a heap sort or something very complex. But doing such calculations can really give you insight about what it is that an algorithm actually does if you write it down very precisely. So if you're stuck, and I really sometimes do this, if I'm stuck, I go away from the keyboard and I try to just draw something up, or I really try to precisely write down what the problem is I'm having, and that can really help even if you don't do a formal derivation like this. Also, this is sort of a general life choice or a general programming advice: delay choices where possible. So in the situation, I don't know what to do, let me just introduce a puzzle here and I'll figure the rest out later. So first I finish the general case of my proof, and then I can prove the rest of the proof obligations later. This is also a technique that is way more broadly applicable than just in program derivation. So that was my talk. Again, this is me on Twitter. If you like this talk, then please tweet it. So other conferences also invite me, because I love going places. And again, if you want to check it out, if it was maybe a bit too high-paced for you, all the slides are on my website, so you can step by step go through it. And also, I highly encourage you, all the things where I said, hand waving, this is obvious, you trust me, send me proofs. Write it on paper and tweet me your proofs, because it would really be cool if you exercise with it.